for coming back to the causal seminar. I'm really happy to have Panos here. He gave a presentation yesterday. He's giving one today. Panos is a good friend. I did my postdoc with him at Booth, and he is going to talk about why we don't need to make the normal errors assumption on regression models anymore. Panos, thank you.
Yeah, let's have the talk. So, okay, thanks everybody. Today I want to talk about what I call residual randomization inference. It's a project that's, it's been a good part of my work really. This is really the third year, and very recently I got some results that I'm genuinely excited about. This is not strictly a causal talk. This is motivated by randomization inference, which is very very popular in analyzing data in experimental studies. But you can think of it as, first of all, yeah, it's motivated by this type of causal methods. But you can also think of it as an attempt to bring those methods to observational settings, like observational studies. So that's the first attempt in doing that. So even though I don't talk today about a specific causal problem, like a specific causal method, it's motivated by those problems, and still I can think of it as an early attempt to bring some of those methods, randomization methods, to observational studies. Certainly, this is the end goal. Okay, so what I'm trying to do here. So let's kind of consider the non-parametric regression setting, right? We have yi is our outcome. There's a possibly nonlinear function covariance xi. There are some unknown parameters beta, and there are some errors that are unobserved. Okay, so I observe the y, I observe the x's. I don't observe the errors. So I want to do testing on the betas. This will be my primary goal today. You can also do inference, but this will come later. So I want to say something about those betas, but I don't want to assume anything more than what I have to assume. So I don't want to assume independence of the errors. I don't want to assume that they are normal. I don't want to say anything about that. I don't also want to say anything about the distribution of the x's. Okay, so the joint, I don't want to impose restrictions on the distribution of the x's and the errors. I'm only going to use what I call structural assumptions on the errors. Okay, only that. So what is a structural assumption? Well, think about any complex dependency on those errors. Okay, there are many examples of that. Probably you've seen, especially if you do applied work, you've seen that before. One structural assumption is that the errors are exchangeable. Okay, so you can just permute them, and their distribution is unchanged. So, for example, when we say the data are IID, immediately we also assume that they are exchangeable. Okay, it's buried in there. So we can also say that the errors are exchangeable. They're not exchangeable, but they're also sign symmetric individually. Like think of heteroscedasticity. Like when we assume that the errors are heteroscedastic, this is what we're assuming. And we cannot exchange them, but at the same time, any sign flip also has the same probability. You also have seen perhaps clustered errors. Okay, so maybe these conditions, these invariances hold conditional on some clusters. Like suppose you have data on schools, so then you cannot. The errors are not really exchangeable across schools, but perhaps they can be exchangeable within schools. Okay, because perhaps there is some idiosyncratic component in the error, like a school-specific error component, let's say. Or you can have doubly clustered errors, right? This can go on, and this can become more and more complicated. Like doubly clustered errors you can have perhaps in trade data, where you have country A, country B, and then you kind of set up a regression model. And now you can expect that these errors might have some complex double clustered type of dependency. Okay, so this is what I call a structural assumption on the errors. The fact that the errors are going to obey, you can write all those assumptions, you can write them kind of using that terminology where basically we're saying that the errors, if you are going to have the same distribution, or the distribution of the errors is unchanged, if you apply a certain transformation to your errors. Okay, so I'm going to assume this script G as an algebraic group of transformations. Think of permutations. Think of just sign flips. Think of within cluster permutations. So any transformation you make from that group on the errors is going to leave the joint distribution unchanged. Okay. So think of the errors, let's say, being normal. Right. This G now can be suppose these are independent normals. In this case, you can just completely flip their signs. The distribution is unchanged, right? Because the normal distribution is sign symmetric. But sign symmetry is a more general assumption, right? Because the same holds for, let's say, t-distribution, which is more heavy tail, but still is sign symmetry. So you can see that now the structural assumptions are going to be more lax, right? Going to be looser. It's going to give me kind of weaker conditions, hopefully. Now, my main inferential assumption is going to be this. The structural assumption is that there is some script Z group that I'm interested in, transformations, and the errors are invariant, distributional invariant to that transformation. This will be, and now the question I'm going to ask is, can I do inference under this assumption, under this weaker assumption than, let's say, IID? What are the limits of inference, if you will? So this is what I'm trying to investigate here. So this type of expressions here, these are not new, really. Like if you're familiar with randomization inference, like the original Fisher papers or the more recent Lehman and Romano framework, randomization inference, which is especially used in experimental settings, kind of work with this type of assumptions where instead of errors here, you probably have a treatment assignment, right? In many cases, when you have an experiment, the experimental assignment satisfies some structural assumptions. For instance, that the treatment is exchangeable, it's permutable. Okay, so you kind of write it like that. Instead of the errors here, this is the treatment. And then they proceed to do the analysis. This is what we call randomization test or randomization. Okay? And it has really nice properties, but it's restricted to experimental settings. And so part of this work today is to try to extend this framework to the setting of observational studies, which here, or an especially model-based approach, where I have a model and I want to impose that assumption not on a treatment assignment, but on the errors of my model. Okay, so how much can I use from this literature in that new domain? And why do I do that? Is because these randomization inference methods, they do have some really nice properties, which I'm going to explain soon. Okay. So the method I'm going to call, like this method that takes the randomization inference from experimental settings to observational settings, I call it residual randomization because it's going to be based on the residuals from my regression. Okay? This is RR, residual randomization. And in summary, what I claim here is the following, that first of all, as a method of inference, it directly compares to Bootstrap because it's generally enough to be applied to many different settings. Okay? And there are four main points here. I think the first three are perhaps the most important on how it compares with Bootstrap. First of all, you're going to see that the residual randomization is going to have it's going to require much milder conditions on the errors and the covariates indexes. Most of these conditions are going to be on the leveraged structure. I'm going to make that precise soon. Bootstrap, on the other hand, usually, at least in main theoretical results, they do rely on square root of n asymptotic normality. So how they work is basically say, here's the my target distribution. This is square root of n of that. It's in the limit is normal. Here's the Bootstrap distribution that also converges to that same limit. So I can use the Bootstrap distribution to say something about the actual sample distribution, right? That's how it works. But at the heart of that, of the proof should be, and the idea is that square root of n asymptotic normality. And in order to get square root of n asymptotic normality, you really need very strong assumptions. And I'm going to make that very concrete soon. Also, what's perhaps more important to practitioners or other people who are interested in the theory of things, residual randomization is going to be one single procedure, basically. So I'm going to pose it for all of these settings that I described earlier with exchangeability, heteroscedasticity, single clustering, double clustering. I'm going to use the exact same procedure for all these cases. What is going to change only is that script G. So you change the script G, that assumption on the structural assumption, but you still plug it in through the same procedure. On the other hand, Bootstrap requires a different variant for its setting. And that's why we have the so-called Bootstrap zoo, right? Because there's a wild Bootstrap, there's a residual Bootstrap, there's the pairs Bootstrap, there's the pigeonhole Bootstrap, there's the wild class of Bootstrap, so there's the block Bootstrap, there's a ton of different variants of Bootstrap methods out there. And you know why? It's because Bootstrap is kind of starts, it takes the, I think it starts, first it starts with the procedure and then it thinks about what is the structural assumption behind my data. What's the structure behind my errors, let's say, or my data. So the original definition of Bootstrap is just resampling, right? Which is exchangeability. So when exchangeability does not hold, you have to change the procedure and you have to change the theory. So in some sense, Bootstrap has things reversed. So you have to, in my claim here, you first need to start with what is the structural assumption and then think about the procedure and not the other way around. So that's why now we need an entirely new Bootstrap for each in every different setting there. That's why we have so many different Bootstraps, and what I'm going to propose is going to be just one single procedure. And in most cases, actually, what's something that's more kind of a new results, which kind of make me like generally excited, is that the residual randomization procedure can also be valid in high-dimensional settings. In the sense, the exact same procedure is valid in high-dimensional settings. In the sense that when p is less than or equal to n, like the dimension of the features to covariance is less than the number of data points still, but still we allow for the number of features to grow. You try to do that in Bootstrap, for Bootstrap you can't, right? You need a new theory, you need new variants, so every new setting requires a new Bootstrap procedure. And again, it's because Bootstrap starts with exchangeability, some IIDness. And so if that doesn't hold, then you have to reverse completely the procedure and try to adjust it. I'll show that in the case of exchangeable errors, actually. And finally, in some limited settings, the residual randomization can even be finite sample value. I'll give you an example that comes straight from the Angry's textbook. I don't think it's more generally applicable. I don't think will be more generally useful, but still it's a neat, I think, fact that can be applied in some real problems as well. So overall, what I claim here is that the residual randomization is robust. It's a principled way of doing inference, and perhaps there's life after Bootstrap, right? That's the whole point. And perhaps this makes it easier for applied research, right? Because as you can see, that there's one procedure, and then what it requires from a researcher only to think about what structural assumptions make sense in any given problem, and not care about the procedure, which I think is much better, much easier, more straightforward, and more principled than the other way around, than having researchers kind of have a complex problem and then try to find what Bootstrap do they need, and then whether they need to adjust Bootstrap in their own way. Okay, so I'll try to make these claims concrete. So I'll try to support this with arguments. So the outline for today is the following. I'm going to describe first of all what this procedure is, this residual randomization that I advertise so much. I'm going to give you the main condition for validity. It's pretty, it's not math heavy. It's just I think it's very, very intuitive. I'll try to give you some also visual intuition of why that holds. And then I'm going to pivot to the linear model. So kind of move from this non-parametric model, kind of pivot to the linear model. I'm going to show you what these general conditions of validity, how they translate in the linear model. And you'll see that in this translation, we get some really simple, really intuitive conditions for validity in linear regression. And then I will talk about clustered error structures, and that's kind of, I guess, less important. I'll just show you how easy it is to apply this method in kind of more complex error structures. But the meat of the method is here in the first few parts. I think the neat kind of conditions, the robustness properties are here in part 3. Part 4 will show you that how versatile this method is. Okay, so let me start with the method first. So suppose we have an assumption. Again, we're still in that general model. We have a null hypothesis H naught on the betas. So how does this method work? First of all, we're going to assume that we can find a test statistic, T of n, some function of the data, such that when the null hypothesis is true, it is a known function of the errors. Okay? So I want to come up with a test statistic. I need a test statistic in order to apply this method. I need a test statistic such that when the null hypothesis is true, it is a known function of my unobserved errors. Okay? This doesn't mean that I know the errors or observe them. I can only calculate it under the null and only for the observed data. Okay, here's an example just to make that clear. Suppose f is linear. Suppose we're testing whether some slope is equal to 0. Then take the OLS slope. Okay. Now, standard theory tells you that if the null hypothesis is true, this OLS estimate is that familiar formula from OLS theory. Okay. So it's just a known function of the error. So I know this. I know this x is. I don't know the errors, but at least I know what the function is. Right. I can just write down what that function is. I don't have to know the errors. I just need to know all the other parameters, which I do. I know the actors and I know this coefficient. Okay. So there are other cases I can come try to show you cases from like time series analysis and other things, but this is perhaps the simplest. This is what I'm going to use in the linear model anyway. So I'll just keep it at that. Okay. So suppose we have come up with a statistic that such this condition holds. Then what you have to understand here now is that now we can leverage this structural assumption of the errors. Now I know that my observed test statistic has the same distribution as Tn of the errors, where the errors have been transformed by any transformation in my set. Okay, just because my errors, this T of n is equal to Tn of epsilon, so any transformation you make in the errors have the same distribution, and so if you pass it through a function, this test statistic function is going to have the same distribution again. Okay, so now for any g, for any transformation, you have two quantities that have the same distribution, and now you can construct a randomization test. What is a randomization test? Here's the very simple idea. You can look into the classical textbook of Limman and Romano, chapter 15. But basically tells you that if you want to test this null hypothesis, just calculate this p-value. Basically, go through all the transformations, calculate the test statistic value of your errors, and then compare it to your observed quantity. And that's the randomization p-value. If that's less than alpha, you can reject. Okay? It's as simple as that. It's a very simple numerical calculation. Okay, so this is still standard theory. Okay, this is the proof of that is also in that text. This is what we do, what we call randomization. Now, why do we care about that? Because it has some really excellent properties, which really shine, especially in experimental studies, randomized studies. First of all, it's finite sample exact. I make no assumption about the statistic here, that it converges, that it behaves well, that it's continuous, that it's smooth, that it's asymptotically normal. None of that. Any function is going to do as long as the original condition holds, and and my test is going to be valid for any finite n. And of course, this adds a lot of robustness, right? Because I don't require anything from the x's, I don't require anything from the errors, I don't require anything from that function, and this works for any finite n. So this is extremely robust to perhaps heavy-tailed errors or heavy-tailed x's, right? Even in this kind of like a kind of tough settings, tough cases. It's assumption-free, right? As I said, I impose no conditions on the error or the x's. And second, is very easy to implement and also communicate. Okay, so this is really what it's doing is, if you think about it operationally, so you have to kind of think of that T of n function being that here, that just the OLS estimate. So basically, what I'm telling you is, you take this OLS estimate function, you take your errors. You commute them, if you're assuming exchangeability, you commute them, and then you pass them through OLS again. And then kind of keep repeatedly do that and compare your observed value with test statistic. Okay, it's extremely simple and it has all this nice properties. Okay, now this works in experimental studies and it's great, right? It's finite sample validity. However, here the problem is that we have a model right now, and the errors are unobserved. This method here is completely infeasible because these errors, I cannot calculate this function, right? Because these errors are unobserved, right? So how can I compute errors that I just don't know what they are? And so the idea now will be to try to approximate that test here by perhaps plugging in the residuals. Okay? So the whole point will be, how does this kind of screw up my test, if you will, right? If I instead of the errors, I plug in the residuals, I get an approximate randomization test. So how bad is this approximate randomization test compared to the let's say the golden standard here? Okay? So you can think of this one as the infeasible test, the gold standard. If I plug in residuals, how bad is it? Okay, and this is part of that what I said earlier. Like I'm trying to bring that randomization inference idea to observational studies, like to model-based studies. Okay, so here's a procedure, and this is the main residual randomization procedure. This is really methodologically, that's the main contribution here. That's the main proposal, if you will. It's extremely simple, as you're going to see. Additionally, what I need is just an estimator of my unknown parameters. Okay, just an estimator. However, I don't insist that this estimator is consistent. I don't even want this to be normal. I just want this to be some kind of estimator of my beta. And the better this estimator is, you'll see that the better the procedure is going to be. But I don't require any assumption of my estimator. So then what you can do is basically in that previous procedure, you take your estimator, you calculate residuals, and then plug in the residual. And that's it. That's the residual randomization method. So here's like how it works in 4 simple steps. You kind of take your estimator. So here you can ignore this linear model. You can take the non-linear model as well. So you take the residuals, you calculate your test statistic, and then you calculate your statistic value across transformations of your residuals now, not your errors, because these are not there, but of your residuals, okay? And it's fine if you take just a subsample of them, like R, okay? Just 1,000 at random, like 1,000 permutations at random, let's say. That's what we'll find. No need to consider the entire space. Then you calculate the p-value exactly as it's supposed to be, and that's your test decision. If the p-value is less than alpha, then you're going to reject your results. That's it. Okay? So it's the simple idea of the randomization test, but you just plug in the residuals from some estimator. So now that's an approximate randomization test. I call it residual randomization because I'm using the residuals in that procedure. But now the question is, of course, now I have an approximate test, approximate randomization test. Is it really as good as the infeasible test? What am I missing by plugging in the residuals? Okay, how am I screwing up this procedure? Of course, first of all, we're kind of losing these nice properties, right? I advertised this, the original method. I said it's finite sample exact, it's assumption free, etc., which is all true. That's standard theory. But now the moment you plug in the residuals, it's this claim no longer. Okay, so the question is, okay, we're losing finite sample validity, but what do we still can hope for? Can we hope for asymptotic validity? That's one. Or can we hope for robustness? That's another one. Because remember, the original test has nice robustness properties. Like if I plug in residuals, does it still have nice robustness properties? So this is like part of my theoretical investigation here. Okay, that's coming up. Okay, so what the question about validity? I know that this residual randomization, because I'm using this approximate residual, this approximate errors, I know that it's not finite sample valid, but it's going to be valid in the limit. So it turns out that there's a very simple condition for which this randomization test is valid. And the condition is the following. Actually, it's two. I'm going to skip that one. This is avoiding some really nasty cases where your test statistic values are identical. This happens with probability 0 when the errors are, let's say, continuous, any continuous distribution. So it's a really, really mild assumption in general. What is really important is that condition over here. So delta n, what you see here is that expression is a random variable where you calculate your approximate your test statistic value from the approximate test, and you compare it to the actual value from the infeasible test. Okay, it's the difference. You can think of this as the approximation error that you make when you plug in residuals. The second quantity here, this lambda, this is the spacing between the randomization values of the infeasible test. So this condition here, that this goes to 0, essentially saying the following. It's very simple, very intuitive fact. That the variation of the approximation dominates your approximation error. That's basically what it's saying. Okay, or the variation, the variance of the spacings in the infeasible test, it dominates the variance of the approximation error. This would be infeasible. Sorry. This is just a very simple condition on the variation of the infeasible test, and then the errors that you're making by plugging the residuals. That's it. And this has to hold in the limit also. This is general, of course. It might look abstract, but when we move to the linear model, you'll see that this reduces some really simple, intuitive, interpretable conditions just on the errors in the features, your covariates. If this condition holds now, then your test is asymptotically valid. Like in the limit, we're not going to reject more than alpha, okay? As the sample size grows. And this is the only thing we can hope for, right? That asymptotic validity. Now, here's something notable. I don't require beta hat to be consistent, or even to be well behaved, or be like a square root of n estimator or something of that sort, which is what bootstrap requires. Okay, this holds. Actually, what this is really telling you is that beta hat has to be good enough such that the approximation error has lower variance in the limit than infeasible test error, like the idealized, the gold standard, the idealized test. So as long as somehow your estimator is able to reduce that variance just by a little bit, just enough so that this condition holds, then we have a valid test. So really general condition thing. Here's intuition why that works. Sorry for my abysmal visualization capabilities. That's just basically Google Paint. What is this? So what do I put here on the top? I put the randomization values from the infeasible test, the golden standard, let's say. These are completely unknown to us, right? Because we never get to observe this absolute. What we can calculate are these red quantities. These are the test statistic values using the residuals, these epsilon hats. Okay, and hopefully these values are going to be close to the randomization values from the infeasible test. Okay. So now that difference here, for example, is just one realization of the approximation error, the delta. The difference between the infeasible value and the approximate value. Okay, this is the delta. The lambda, the spacing, is a difference between two values in the infeasible test. It's the lambda and the delta. These are the important quantities for validity. Now think about the following. A randomization test it relies only on the quantiles of the randomization distribution, right? Because we're comparing, if you remember, we're comparing just the ranks of that distribution with what we observe. Now the quantiles of the infeasible tests, and so the test decision, the quantiles of that black quantities here, they're generally very similar to the of the red ones. They're very similar to the infeasible test, like the black ones. So the quantiles you get from the red, which is the realized, the feasible test, these are going to be, the quantiles are going to be very close to the ones from the infeasible test. As long as this approximation error is dominated by the spacing. Okay. In fact, you can very easily show, like with algebra, that the quantiles are actually identical if the maximum error, approximation error, is dominated by the minimum spacing. So think about it. So what happens here is that I have an infeasible test, and then I try to approximate those values. Okay. If this approximation error is smaller than the minimum spacing of those these values from the infeasible test, then this error doesn't matter, right? Because it's a smaller, it's not big enough to matter for the quantiles. So it's not a problem that I'm using just an approximation here, because my error is dominated by the spacing of that infeasible test. That's it. And so this relates to you can actually show that the sufficient condition is just that variance dominance condition. And this also explains why these randomization tests are so robust. It also explains why they can be robust in these observational settings, in this approximate sense, not in the actual the infeasible sense, but also in the approximate sense over here. So it shows you, I think it's also for the first time in terms of the theory of randomization inference, I think it's probably one of the first few works that kind of show the benefits of randomization methods for the approximate randomization methods, okay, where the conditions don't really hold the same. Okay, and it's exactly because of that, because I don't have to really pinpoint the true values of my randomization test. It can tolerate some approximation error, as long as this approximation error can compare or is dominated by the spacings of that infeasible randomization distribution.
So can I ask a question?
Yes, of course.
So like in a linear, just make sure I'm following. In a linear model, the reason you need that weak condition on data is because all you need is this approximation error to know. Because that approximation error is going to be a feature of your estimator for data.
Yes, it's going to be a feature of the x's and the error distribution
data. So the condition on data basically means this approximation error can't get so bad.
Yes,
and that's
the only thing that's needed.
Specific condition on data.
Yes, that's needed. Yes, and also, and mind you, this is not telling you, this is not requiring that the estimator is consistent. Right.
Just that it can't be so
just
bad.
Yes, exactly. Right. Exactly. Yeah. So the test can tolerate a certain amount of approximation error. Of course, if it's too large, if this delta is much bigger than the spacing, then it is going to mess up. Yes. But if it's not, then the approximate test is going to be very similar to the infeasible test. Exactly. I'm going to make these things concrete with the in the linear model version. That's a good question. I can also get finite sample errors, like how bad is this, my overcoverage perhaps or undercoverage. Well, it turns out there are two quantities that matter. One is the spacings, some parameter on the CDF of the spacings. I kind of use this gamma here, and also this the rate at which this kind of ratio converges to zero. That also matters for the amount of misspecification of the overcoverage or undercoverage of my test. And this is the quantity. So I guess I can try to make it a little simpler. So this gamma here that I'm using essentially controls how big these lambdas are. Okay, so when you have these gammas are small, so when the distribution of these spacings give you spacing that are very small in feasible test, then the rate goes down. So it makes, of course, the approximation harder. So just to give you some idea about what this theorem is telling you, under regularity conditions, this is going to be 1/n typically, and then this gamma, suppose you have a test statistic that's normal under regularity conditions, this gamma is going to be 1. So the rate to validity is going to be -1/3. Okay, it's pretty slow. And actually, the best rate that you can get is when gamma is like very large, which would be -2 to the third. Again, very slow. There are in bootstrap theory there are some terms like first order correct, like things like that tell you that the rate is of kind of testing validity is like 1/n. This shows you cannot directly compare it to bootstrap, but this more or less shows you that the randomization test it pays a price for having that robustness, and that price is kind of slower rates of convergence. That's more of a theoretical interest in this. Okay, so let me pivot to the linear model, because now the assumption, this is a very general assumption of, and actually it's an umbrella theory, if you want, like a theorem about the performance of an approximate test, an approximate randomization test compared to an infeasible test. So let's look into the linear model and see how this translates into the linear model. Okay, what kind of conditions did we get? Essentially, what I'm going to do is I'm going to tell you this condition here, what it reduces to in a simple linear model. Okay, you'll see that it becomes empirical. So this is a linear model that I'm going to focus on. I'm focusing on a linear hypothesis. Just the linear combination of the betas equal to some known value. The simpler case is when you're testing its component, whether it's zero. That's a simple significance test. Let's say our test statistic is going to be equal to that quantity. Just plug in the OLS estimate, and of course this satisfies our assumption, because under the null hypothesis, this T of n is equal to that function of the errors. Okay, so it's a known function of the errors as it's required. Also, you can take that test, and you can also divert it to get converse intervals for your betas. Okay, just to test many possible values to the betas. That will come up a little bit later. Okay, now I'm deciding I have the linear model, I have a null hypothesis, just let's say a significance hypothesis on the slopes, and I have a test statistic, and I know that my conditions are. So let's now see what conditions do I need in order for my residual randomization test to be valid. So let's start with exchangeable errors. Okay, let's assume that the errors are, if you just kind of permute them, they have the same distribution. So you can write it like this, like the error distribution, kind of permute the errors, they're going to have the same distribution. Let's say this is the same, it's not the same, but when you assume IID errors, you can also assume that exchangeability. Okay? It turns out that in the linear model, and assuming that the errors are exchangeable, the only condition that you need, that condition of this variance dominance, the condition is that your P, your dimension of covariance, over n, the number of data points, is little over this dimension, it's close to 0. So that it's, over, as I told you this, over these 3 years, I've been kind of reducing those conditions, and I was really generally excited that it ended up in that. Like this is a kind of a relatively new result, which made me generally happy, kind of because it shows so many different aspects of that problem, so many different aspects of the benefits of that. First of all, clearly you see there are no conditions on X. There are no conditions on the error distribution, and OLS could even be inconsistent. How can it be consistent? Well, think about errors that increase in variance. Why not? So why do we assume that the errors have constant variance all the time, or they have heteroscedastic variance, or they have bounded variance? Perhaps it increases with them. The more samples you get, the more variance you have. Okay, that's fine. In this case, the OLS will be persistent. Still, your inference can be fine. Okay. You also get validity even when the dimension of covariance goes to infinity, as long as it increases at a lower rate than so this is a high dimensional setting. It's not the p bigger than n high dimensional setting, but still it's some sort of high dimensional setting, right? And I think it's really remarkable that it kind of you kind of get it for free basically with the same procedure. There's no, I'm not using any other estimator here like high dimensional estimator or anything else. And I think more philosophically, it shows you that, I think the theorem shows you that exchangeability is really a strong inferential assumption. It shows you that perhaps exchangeability already puts a lot of structure. It already includes a lot of structure. So it's already a very strong assumption. The fact that it reduces to this condition only, perhaps it tells you that it already puts a lot of structure into your data. So that's a more philosophical interest, right? And that's something that I've noticed in experiments too. Like you can get the same inference when you assume IID normal, and also you kind of also assume, and you run classical OLS, and then you do this residual normalization only with exchangeability. You get very similar inferences under typical conditions, which means that exchangeability is enough to get you, like most of your inference. The rest is not new. Okay, and how do you compare it with bootstrap? Well, remember this bootstrap principle tells you that the square root of n asymptotic bootstrap distribution is the same as the actual sample distribution. The problem is that you're not able to calculate that, so you kind of rely on the bootstrap distribution to do it. However, in order to get that, you need some good asymptotic behavior of beta hat. Okay, so if you look into a paper of the so-called residual bootstrap by Friedman in the 80s, which is perhaps the closest bootstrap variant to this exchangeability test that I mentioned. In order to prove that the validity of the residual bootstrap requires IID errors, mean zero, finite variance, and also requires a limit for this run matrix. This also appears a lot in standard OLS inference. We usually assume that this XDX this Graham matrix has a limit, but why should it have a limit? There's no like fundamental justification why these things would have a limit, right? So these assumptions are extremely strong, I think, at least compared to the residual bootstrap that gives you validity only with conditional P and N, basically. And of course, requires this P to be finite, right? And otherwise, you don't even have a limit. That's a side. So I think the comparison is pretty stark between this residual bootstrap and the residual normalization. And it could be theoretical. It could be because of the theoretical, because the theoretical analysis of bootstrap is not kind of didn't follow that didn't borrow stuff from the randomization theory. So perhaps bootstrap can do better. I'm not sure about this, but this is really the I guess state of the art knowledge about the bootstrap. So and bootstrap is usually used in that way. So, okay, so here's an example that I tried. This is one of the worst examples could come up with. We have T distributed X's, a very heavy-tailed error distribution label, and I get this P to be square root of n. I can keep increasing the dimension of the X's, and I'm kind of running residual normalization. You see that kind of drops down kind of steadily to 5%. Okay, of course, as you keep increasing the replications, as you keep increasing n, this is going to get to 5. But already you see that even with like super heavy-tailed data, even with a high-dimensional, quasi-high dimensional setting, the residual normalization gets to asymptotic validity in the expected range. Okay. So seems I'm running kind of late, but this is really, I think, parts 1 to 3. The rest are going to show you how this method works in other more complex settings. So I guess I can take a pause here. If there are any questions about this simple, let's say, exchangeability settings where I have perhaps compared with Bootstrap, really the method is this. It's actually, you can implement it in a couple of lines. Okay, so I can take some questions here before I move to the cluster errors. Or if there are no questions, I can just keep it. Yes.
I have a question on the assumption.
Yeah.
So,
You mean
yeah,
this one?
G function.
Oh, in the beginning?
Yeah, in the beginning.
This one.
Yeah. So, is the assumption that the residuals are transformable, or is the assumption that the function G is known?
Yes, good question. So I should clarify that this assumption is on the true errors. It's not on the residuals. So the residuals are going to have going to depend on the data. They depend on the x's. So they don't, in general, they don't satisfy that assumption. But I'm assuming that the errors in my model satisfy that assumption, that somehow the errors were generated through some DGP that is exchangeable, let's say. Perhaps this data are, perhaps the errors are measurement errors, right? You have a telescope kind of, let's say, observing the planet, and there's always some noise, white noise. So I'm going to assume that this white noise is exchangeable, or it's symmetric around zero. So I can impose this kind of structural assumptions on these unobserved errors. I never get to test that though. This is a structural assumption that this is you have to take just to get to do your inference, right? It's never like kind of fully testable. You can have diagnostics, but it's not like fully testable because it's an assumption on the unobserved errors. Okay. And this is and then your second question, yes, you know. So I know that, and you can think of it as also as an analyst, you might say, okay, this is what I think is the structure of my errors. I think they're symmetric around zero because it's just white noise. So my G here is going to be any sign flip, basically, of my errors. Okay, so G is known and it's set by the analyst, let's say the data scientist.
But I was just trying to understand that why would the approach that you explained fail if this assumption is not true?
Oh, if this assumption is not true, even in this feasible test, that will fail, right? Because eventually what we're comparing is that we're comparing the observed value of the test statistic with the value of the test statistic where the errors have been changed according to G. Now, if these errors, if you transform them according to G and the distribution changes completely, then these are not directly comparable. So even the infeasible test is going to break down, let alone that approach.
Do you have any more I guess philosophical thoughts as to just a trajectory of statistical inference starting from us making a normal distribution assumption, and then we can kind of write down all these complex zones and everything, and then we have the bootstrap, right? As soon as we're able to run things on computers, and then I kind of see, so basically, as I think about this through time, right, we're kind of now moving from bootstrap to this much more simpler world where I have exchangeable layers only. And I'm wondering if you think that do you ever think about that? And is this like, do you see this kind of becoming more of the norm?
Yeah, I think part of this specific path has been that we were never, at least in the early days, we were not interested about the clustering of errors, right? We're not interested in the complex structure of errors, I think. So we were fine kind of doing inference with just IID data. So that's how I think that the bootstrap was very natural, because we were assuming that we still do, right? Like machine learning never talks about cluster errors, really. So it's a concept that's mostly used by economists who deal with real data. And they have noticed that in the real world, we don't have this nice IID, this assumption, exchangeability assumption. So I think the problem was that we never started with that complexity in mind. And so it was an afterthought. So the bootstrap was developed, and now we have to deal with all these complex structures. We have to kind of adjust it, right? And I think the problem was that bootstrap came first than this. Actually, the randomization method is even earlier than the bootstrap, but it kind of stayed. For some reason, it stayed in the experimental world, like an experimental design world. It was never used for inference in that way, even though it's perfectly fine, right, to use it. So yeah, that's why perhaps it's just a matter of chance that first the bootstrap was developed that was heavily dependent on IID and assumptions, and so then And now we have to backtrack, right? We have to deal with those complex structures. But,
And then second question, what are like the computational bottlenecks? Like what if I have a test statistic that is computational, challenging to compute? Yeah, where are I guess the future directions in this? Where are you missing the more machine learning world?
Yeah, that's a good question. To be honest, in terms of practice, I've only used it in the linear model, like the different structures, and there the computations are super easy because it's just all less, right? If it's something more complex, then it can be an issue because you have to calculate it for like many times, right? Like 1,000 times. But the good thing is that you can completely parallelize this. Like these are samples that you have to calculate. This is really the bottleneck. So if calculating Tn is the problem, you can use 1,000 nodes and do this at once, right? So it is embarrassingly parallelizable in that sense, as many randomization methods. But I haven't come up with an example where this T of n is something really computational. Right? Yeah, it's because I've stuck to the so far with the linear. Okay. All right, so I have 5 more minutes, so I'll try to spare you. Won't waste more of your time. What I can talk about is just the clustered errors. And I just wanted to show you from that is, I have discuss some conditions of validity. I guess what's more important is the simplicity, the versatility of that method, like how easy it is to address problems where we have this complex structures. So what is clustered errors? Well, if you deal with data, sometimes you have you know that the data come from a state, right, or from a school or a grade, and applied researchers are kind of worried sometimes that the errors might be clustered by state or by school, right, or by grade. What this means is that there might be some idiosyncratic components of the errors, like specific to the school, like specific to the grade. And the major problem is that when you ignore this clustering, essentially you are kind of assuming that you have more data than you actually have, right? Like suppose you have data from just one cluster, and for some reason all the errors from one cluster are super highly correlated, right? So essentially then you have one sample, you don't have n, you only have one sample. So it's very easy to kind of overestimate your confidence. So people have developed cluster robust methods. I'm not going to get into the analytical methods because these are extremely complex. They have well-known problems with small samples, normality, etc. I guess what people trust the most is the so-called clustered wild bootstrap. It's an alternative, but it here at least works under strict conditions and cannot be easily extended in other domains. So what can we do? How can you apply a residual randomization in this case? Well, just think about philosophically, if you will, you think about what kind of transformations, what kind of invariances make sense when you have cluster data. For example, perhaps you could assume that your errors are exchangeable within clusters, not globally exchangeable, but perhaps within a school, the error of measurement is just completely exchangeable within each school, okay? Or perhaps you can have symmetry across clusters. Perhaps we can say that there is some form of sign symmetry where I have cluster 1, cluster 2. I can multiply with just one same random sign every cluster, like all the errors in one cluster, and that has the same distribution of my residual errors. That's a sign, what they call sign symmetry across clusters. It is essentially what cluster-wide bootstrap does. Cluster-wide bootstrap does not resample all of the residuals or all of your data. Basically takes residuals from clusters and then multiply on the cluster level by plus or minus at random. That's the cluster wild bootstrap. And wild bootstrap is this random sign business. Cluster wild bootstrap takes that business into the cluster domain. So even the names are, I don't really like that. Wild means nothing. Wild bootstrap. Anyway, or you can assume both invariances, right? You can assume that the errors are exchangeable within clusters, but also there's some sign symmetry across clusters. You can mix and match, if you will. It's up to what you think. It's up to the scientist, I think, to determine that. So how can you apply residual randomization? It's actually quite simple. There's nothing that you can still apply that procedure over here. The only thing that changes is that this little g, you just make sure that you permute within clusters, or you kind of swap signs across clusters, or you do both. That's it. This is what I said, this unified way of inference, like one single procedure. I really meant it, right? So you just plug in your G, and you just use the exact same procedure. You don't have to use it as in Bootstrap. You have to come up with something entirely new. So the moment you define these G's, then you apply this residual randomization method, and then you kind of hope for validity. And I can show you quickly soon what these validity conditions are. Here's an example, just to, if you haven't worked with clustered errors, kind of just to illustrate the types of problems. Suppose you have a model where you have the slope here is 0.2. You have your errors have two clusters if the x is small. So basically tells you that there are two clusters here, and one cluster has a much larger variance in the errors than the other. It's a very simple setting where two clusters, they have just a heterogeneous variance. You try to run OLS, you just get no significance for your slope. Why? Because OLS ignores the cluster structure, right? Of course, this variance in the second cluster is going to propagate, is going to spill over in that first cluster as well. So that's why OLS finds no significance. What can you do? Well, you can see here that in this model, we know what the clusters are, and just for illustration, of course, you can just essentially calculate the residuals and then permute within those clusters, because you know these errors are exchangeable within clusters. Okay, no need to worry about these variance estimates. No need to worry about the sample, their mean. Actually, this means could be different also. It doesn't really matter. What matters is that within a cluster, these errors here are exchangeable. That's it. You don't even need this normality assumption. You kind of pass it through residual randomization, and then you can actually calculate a p-value for your null hypothesis. And you can actually do that for many possible values of your slope. Should you see that? Yeah. Okay. So this here are potential values of the null hypothesis of the slope. You see that it kind of peaks around 1.5, the p-value. The true value 0.2 corresponds to the p-value that's 0.2 something. So this is also not rejected, right? So this is also what I meant by test inversion. Like you can run this randomization test for many possible values of the slope. You can take a look at this p-value, you slice it at 0.05, and then you look into what values of your slope are bigger than 0.05, and that's your randomization from the slope. That's called test inversion. Okay. Here you see that this method uncovers, kind of uses this cluster structure effectively. Okay, it's able to give you a much more essential result. Okay, what are the conditions for cluster errors? It becomes quite more complicated, but roughly speaking, these are the kind of roughly what the conditions are. So when you have exchangeability within clusters, or sign symmetry, or both, you actually have some leveraged quantities for the axis, some leveraged quantities for the error distribution, and then you have some conditions on P, the dimension of your covariates, and then the number of data points. So what is this lambda x? This is usually the condition number of your ground matrix. Usually it is there. It changes by model, but it usually has to do with the condition number. Sometimes it's also the OLS lever, the linear regression leverage, as it's defined in standard way. This lambda epsilon is the leverage in the error distribution. For example, when you have exchangeability within clusters, this lambda epsilon is the maximum cluster variance over minimum cluster variance for your cluster. Okay, so of your errors. So you kind of get this type of formulas, and kind of notice here that these leverages can still go to infinity. Okay, even though under standard regularity conditions, these lambdas are bounded, the condition number is extremely stable as a point. So when you assume, for example, that this xtx is kind of converges as they do in standard inference, then the condition number is bounded. Okay, so under the standard regularity conditions in the literature, these lambdas are basically bounded. Okay, so then you end up with these conditions on the dimension and the number of data points, which is similar to the simple exchangeability. Okay. Now I should mention also that this method of the sign flips across clusters is actually equivalent to the cluster one bootstrap. Actually, these two methods coincide, and so you can think of that of our analysis also as a significant extension of what is actually known. What's the state of the art that's known for cluster one bootstrap? The state of the art tells you that A cluster wild bootstrap can work also with a finite number of clusters, but you need some really strong homogeneity condition of your errors. Basically, that your correlation structure within a cluster is kind of matches the global structure. So we can get away with that and still have validity. So it probably has some theoretical interest as well. Okay, so I'll just skip finite time validity, and actually I'm going to skip also. I have some examples about this finite time validity. I have another example about two-way clustering, and dyadic regression. But I'm going to stop here. I'm going to summarize, and if there are questions, I can talk to you about double clustering, which is again very easily I can do this with this framework. So just to summarize, what I kind of show you today is that this residual randomization inference that hopefully convince you that at least it's a unified way of doing inference, right? That you just have to think about what transformations make sense for your problem, and you just pass it through that same procedure. In contrast, Bootstrap requires always tweaks, always adjustments depending on the problem. In many cases, we don't need assumption on the distribution of the errors or the x's. It can work also in quasi-high dimensional settings. And I think in general, it's a good practice, and also it can be very helpful for practitioners because it just gives them a procedure and only asks them to just think about the nature, the structure of the problem, and don't worry too much about the analysis. I have many simulations. I didn't show you too many of them today, but it does compare favorably to established bootstrap variants, and there are many of them, like wild bootstrap, cluster wild bootstrap. If there are questions, I'll be happy to show some data on that. And also robust error methods, which are generally perform even worse than okay? So hopefully that idea kind of brings some of these good properties of the randomization inference from the experimental world to the observational world, and just one step towards more robust and easier, more straightforward statistical inference. So thanks for your attention, appreciate it. If there are questions, happy to take them, especially about those subjects that I skipped.
Sort of curious, thank you for that. It's really interesting. I'm curious your thoughts on sort of the different types of structures that you could encode into G. So clustering extensions to more complicated clustering, I think you made a case to that. Is a natural thing to include, talk about symmetry. But what about spatial correlation, time series, structurings of errors, things like that, where at least to me it's not as clear how you don't have this discrete G like you would with symmetry or clustering. So I'm just curious your thoughts on how far you push that in your own way.
Excellent. That's an excellent question. I have a backup here about autocorrelated errors, let's say, right? Like suppose you have a time series model now, and you kind of perhaps you're worried that you have some autocorrelation in your errors as well, right? And perhaps you also think that your errors are not stationary, right? You might have this autocorrelation parameter to be non-changing, not being stationary. What can you do here? What's a natural, as you said, like, it's not clear what's a natural idea for definition of that J. Well, here's one idea that I have played around. I have implemented it, and I've tested against like so-called hack errors, like heteroscedasticity and autocorrelated system errors. It performs better, but the theory still eludes me, and I will tell you why it eludes me still. Here it is. Like suppose that you have a condition, an error process like this, where these errors are being zero. Okay. Now, what is the assumption? The implication is that if somehow you hit zero at some point, suppose it's a continuous process, it hits zero at some point, then it's completely symmetric, or it's completely sign symmetric, conditional on hitting zero. So basically, what this means is that if you know that suppose this is your error process, right? And it hits those time points, it means that at those time points where you hit zero, you can completely flip it around. And it still has the same distribution. Okay? And I'm not assuming that it's stationary even, right? That's a natural assumption, like an invariance assumption in this case. So this is actually similar to the cluster, the sign cluster test, because you can think of this as clusters now. What is the and this is why the theory eludes me, because this clustering is now random. because you just don't know these points, right? They're going to change every time. It's not that you have a fixed clustering like in cross-sectional study. So if I can work with this kind of random clustering, like suppose this is not an issue, then this is really saying that just apply this signed cluster residual normalization test, where you think of these observations as clusters. Basically, you kind of move all of them together to the other side, and they kind of do this independently. Why? Because this is really and again, I'm not assuming anything about you except for the sign symmetry. Also, I'm not assuming anything about that coefficient. Of course, I need this AR1 structure, but it still allows me a lot of there's a lot of room here, a lot of that are unspecified. So that's one way. That's one way to define invariances. Theory eludes me, but in simulations, it's here. I compare to hack errors to LS. It really performs. It really performs well, favorably to compare at least to the hack errors. So I don't think it's going to be in this work, but it's definitely something to look forward to. Because perhaps, and you're right, this is really, it's straightforward to how do you define invariances in these cross-section studies, right? More or less we know, but in time series, this is
spatially.
Especially, I don't see how you can do it, unless you kind of are able to find out something like that, right? There's some. I'm not also sure that there are some spatial processes that might have this type of invariances, perhaps, or perhaps you can assume that some regions are completely independent. But I'm not going to speculate that. It might be even. I might not be able to do it.
All right.
Okay. Yeah. Thanks a lot.